Chebyshev filters are an alternative to Butterworth filters, and they are named after the Russian mathematician Chebyshev. There exist many different spellings of the name Chebyshev in Latin letters. A list of those spellings can be found in the script. The Chebyshev filters are based on the Chebyshev polynomials, which are denoted with capital T of omega, and the first one is T1 of omega equal to omega. The second one is equal to 2 omega squared minus 1, and all following Chebyshev polynomials can be obtained from the recursive formula Tn of omega is equal to 2 omega Tn minus 1 of omega minus Tn minus 2 of omega. Here you see the first 4 Chebyshev polynomials as a function of omega. The first one is drawn in blue, the second in green, the third in red, and the fourth in black. They all have in common that t is in between minus 1 and 1 for values of omega less than 1, and t is always greater than 1 for values of omega greater than 1. Also, t is equal to 1 for omega equal to 1. These polynomials can now be used to design 2 different types of filter. The first one is called type 1 Chebyshev filter. The magnitude of the frequency response of the nth order type 1 Chebyshev filter is given by 1 divided by 1 plus epsilon squared Tn of omega divided by omega c squared, where Tn is the Chebyshev polynomial as a function of omega divided by omega c, so again we normalize the frequency here, and epsilon is the ripple control factor. By choosing epsilon small, we can ensure that the ripples in the passband decrease. The transfer function of the first order type 1 Chebyshev filter in normalized S is given by h of omega c s equal to 1 over epsilon divided by s plus 1 over epsilon. The second one is given by h of omega cs equal to 1 over 2 epsilon divided by s squared plus the square root of 1 plus 1 over epsilon squared minus 1 times s plus the square root of 1 plus epsilon squared over 2 epsilon. As you can see, the Chebyshev filter is slightly more complex than the Butterworth filter. The poles can't be easily derived because they are no longer located on a unit circle, but rather on an ellipse around the origin. Through this, the poles can be pushed closer to the imaginary axis, which improves the roll-off without having to increase the order of the filter as much as with the Butterworth filter. As a result of this, the roll-off rate, which is the first derivative with respect to omega of the logarithm to the base 10 of the magnitude of the frequency response squared at the cutoff frequency, is equal to 2n squared epsilon squared over epsilon squared plus 1. So for a constant ripple control factor epsilon, the roll-off improves quadratically with the order n. The ripples in the passband of a type 1 Chebyshev filter are limited to 1 plus minus 1 minus 1 over the square root of epsilon squared plus 1, which is equivalent to saying that 1 minus delta p is equal to 1 divided by the square root of epsilon squared plus 1. This shows that there is a trade-off when designing a Chebyshev filter. If increasing the ripple control factor epsilon, the roll-off increases, but the ripples get bigger. On the other hand, if epsilon is chosen smaller, then the roll-off becomes slower, but the ripples decrease. When choosing a high filter order n, the roll-off increases, but the filter will have more ripples. On the other hand, if choosing a lower filter order n, the roll-off decreases, but the number of ripples also decreases. This can be verified easily when plotting the frequency response as a function of omega for different type 1 Chebyshev filters. Here you see the first order type 1 Chebyshev filter in blue, the second order filter in green, the third order filter in red, and the fourth order filter in black. As you can see, when increasing the filter order n, the roll-off gets improved. but at the same time the amount of ripples in the passband increases, despite the fact that all ripples are bounded by the same value, so that all filters have the same 1 minus delta p, because all those filters have the same ripple control factor epsilon. If we want to design a type 1 Chebyshev filter, we have two design parameters, so we have to choose a suitable ripple control factor epsilon and a suitable filter order n. The ripple control factor epsilon is simply given by the square root of Gp, where Gp is defined as for the Butterworth filter, so that epsilon is equal to the square root of 1 divided by 1 minus delta p squared minus 1. The filter order n of a type 1 Chebyshev filter can be approximated by the formula cosine hyperbolicus inverse of the square root of gs divided by gp divided by cosine hyperbolicus inverse of omega s divided by omega p. Let's look at the example again that we saw for the Butterworth filter, where we wanted to design a low-pass filter with passband ripples of up to plus minus 3 dB, a passband frequency of 1 kHz, stopband attenuation of at least minus 30 dB, and a stopband frequency of 2 kHz. Gp is equal to 1 and Gs is equal to 999. Using the value of Gp in the formula for the ripple control factor epsilon gives that epsilon is approximately 1, which is always true for type 1 Chebyshev filters with passband ripples of up to minus 3 dB. Using the approximation formula for n gives the result 3.1502. Keep in mind that this formula is an approximation, so a third-order type 1 Chebyshev filter might actually satisfy our specification, but there is no guarantee. However, when using a fourth-order filter, we can be pretty sure that our specifications are met. Here you see the plot of the frequency response in dB of 3 different filters. The first filter, drawn in blue, is the Butterworth filter of order 5 that we designed in the previous example. As you can see, it matches the specification. The curve in green is the type 1 Chebyshev filter of order 3. As you can see, it does not quite match our brick wall specifications. But when increasing the order of the type 1 Chebyshev filter, here drawn in red, the specifications are met. There also exist type 2 Chebyshev filters. Sometimes they are called inverse Chebyshev filters. In contrast to type 1 Chebyshev filters, they have a monotonic passband and ripples in the stopband. The magnitude of the frequency response of type 2 Chebyshev filters is given by 1 divided by the square root of 1 plus the inverse of epsilon squared Tn of omega s over omega squared. This can also be written as the square root of epsilon squared Tn of omega s divided by omega squared divided by 1 plus epsilon squared Tn of omega s divided by omega squared. Again, the blue curve shows the filter of first order, green is the second order, red shows the third order, and black shows the fourth order filter. Again, when increasing n, the width of the transition band is reduced. However, when increasing n, the amount of ripples in the stop band is also increased. Since the ripples of the type 2 Chebyshev filter can be found in the stop band, the ripple control factor epsilon is given by 1 divided by the square root of Gs.